Okay, so in the last section we were talking about Fermat's theorem, which said that if you have a minimum or maximum and if the derivative exists, then the derivative has to equal 0. That did not mean, though, that if the derivative is 0, then that you would have a maximum or minimum, right? So we're going to expand on that a little bit and talk about this idea of a critical number. So a critical number is anywhere that the derivative is equal to 0 or it doesn't exist. You might get maximum minimums there. You might get other things like inflection points or something. Different things can happen, and we'll get into more detail in those in the next section. So, but right now, let's just worry about seeing if we can identify critical numbers. So we want, for a critical number, the derivative is either undefined or 0. So, if if it's equal to 0, hold on, my little thing went crazy here because it does that a lot. All right, so if the derivative is 0 or undefined, or it doesn't exist, right? So first thing we do is need to find the derivative. So in this case, that's going to be what? 12x squared minus 12x minus 72. So this is a polynomial, so I know it's continuous and it's a nice smooth curve and all that stuff. So I don't have to worry about the derivative not existing because it exists everywhere. So I just need to worry about where is that thing equal to 0. So I'm going to set the derivative equal to 0 and solve. So I'm going to go ahead and factor this thing. Let's see, 72. Yeah, we'll factor out a 12, and that's going to give me x squared minus x minus 6. Now I need to find two numbers that multiply to be the negative 6, right, but add up to be the negative 1. And so that would be uh, negative 3 and 2. Okay, so setting my factors equal to 0, either x minus 3 has to equal to 0 or x plus 2 equals 0. So that means x equals negative 2 or 3, and those are my critical numbers. So I know when x equals negative 2 and when x equals 3, we got something funny going on in the graph, maximum, minimum, turning points, or something like that. So let's see. Let's do a couple more of these. So let's think about this rational function. So I need to find my derivative, right? So g prime of x, we'll use the quotient rule. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So simplifying a bit, let's see, we get y squared plus 9 minus, now let's be careful. I'm going to make an extra step in here so I don't mess up my signs, okay? Why do I have a 2x minus 3, by the way? It should be a 2y. That's going to be 2y squared minus 3y minus 6y plus 9. Now the denominator, don't bother multiplying that out, okay? Because that's already all factored and stuff, right? So we don't need to worry about the denominator a whole lot. So now when I start combining like terms, we get negative y squared. So let me keep track of these things. So we got that one, and then negative 3y plus 3y plus 6y would be 6y. And then we get a 9 minus 9. And in the denominator, we still have that. Okay, so I need to know where is this 0 and where is this undefined. Okay, so when a fraction is equal to 0, the numerator is equal to 0. So we need to solve this. And then also, where it's undefined is when the denominator is equal to 0. So we actually have to solve that one as well. Okay. So I can factor this and say, okay, well, let's factor out a y that's negative y plus 6 equals 0. So in this case, either y equals 0, or when the other factored is, it's equal to 6. Over here, since it's that squared, really all I have to worry about is this, right? Think about taking a square root of both sides. Then we can try to factor that sucker. Can you find two numbers that multiply together to be 9, but add up to be -3? So your only choices are 1 and 9 or 3 and 3, and that's not going to work, right? So we can use the quadratic formula. So -b plus or minus square root of b squared minus 4ac all over 2a. Okay, so the negative Yeah, 9 minus 4 times 9 be -27. Okay, so this is not a real number. So we don't have to worry about that, right? It's not undefined anywhere. So our critical numbers are just the 0 and 6 in this case. Got a couple other oddball ones. I was just thinking you might not have seen some of these, so we'll do a few more. Okay, how to solve this one? So first off, though, we've got to get our derivative, right? So that's going to be 1/5 x to the -4/5 plus 4/5 x to the -9/5. So how do we solve this? Well, again, we could actually think about factoring, and we want, where is that equal to 0? So I can factor out a 1/5 for sure out of both of those. Now, when it comes to the variable pieces, and I really meant to highlight that, not do a little scribbly thing. When it comes to just these variable pieces, pick the one that has the smallest exponent. So in this case, x to the -9/5. -9/5 is smaller than 4/5. So I'm going to factor out the one that has the smallest exponent. So now remember, to get one in there, what we're doing is we're really kind of dividing, right? And so when you're factoring things out or you're dividing, you subtract exponents, correct? So if I do -4/5 minus the -9/5, and that'd be -4 plus 9 over 5, because I already have that common denominator. And that's going to leave me with 5/5. That's just going to leave me with a 1. Except I did my signs wrong. Shoot, what am I thinking? I'm factoring the 9/5 out, so let me just fix that real quick. That would be yeah, no. I don't know. I just had a brain fart for a second. That was okay. So we're going to have x there, okay, plus if we take the x to the -9/5 out, we're just going to be left with a 4, okay. So that gets us a little factorization. And then we could set each factor equal to 0. If I set each factor equal to 0, then x equals -9/5 is equal to 0, or we get x plus 4 equals 0, right? So in this case, x has to equal 0, or this one is -4. So our critical numbers are 0 and -4. But when you see these with rational exponents, the trick is to, if they all have the x and stuff involved, is to factor out the one that has the smallest exponent. So next in line, we have trig stuff. Okay, so the derivative of cosine is negative sine, so that's 4 sine of theta. Wah! Okay, plus, now remember, this 2 sine squared of theta is really this thing, right? Which is 4 sine squared of theta. What am I doing? 2 sine squared of theta. I meant to write it a little different, then I just confused myself. So see, even at home, I still have my technology issues. There. Maybe that'll fix the scrolling thing. So anyway, what I'm thinking about is, that sine of theta squared, right? So we have to use the chain rule. So that's 4 sine of theta times now the cosine of theta, because you got to do the derivative of the inside. Okay. Now, again, we have a greatest common factor of a 4 sine theta in both cases. So I'm going to factor that out. Say, okay, well, let's have 4 sine theta. And that's going to be a -1 plus cosine of theta. And we want to know where each of those are equal to 0. So sine of theta is equal to 0. Or -1 plus cosine of theta equals 0. So where is sine of theta equal to 0? So remember, I told y'all, remember the unit circle. Okay, and then each of these ordered pairs on the unit circle, that's a 1, 0, is sine and cosine, right? So sine of theta is equal to 0. Sine is the y-coordinate at 0 and pi, and every multiple of pi. Hide that. I don't need to restart yet. Go away. Oh, yeah, it doesn't want to go away. All right, I'm just going to let it go. It can stay in the bottom corner. Crap. Anyway, so sine of theta is equal to 0 at any multiple of pi. So I'm just going to call that n times pi, okay? So over here we'll have, where is cosine of theta equal to 1? Cosine of theta is the x-coordinates, right? So the x-coordinate would be 1 only at multiples of 2 pi. So in this case, every multiple of 2 pi, so 2n pi. Now, the trick is, on this one, we've actually already counted those, right? Because certainly if I took every multiple of pi, that includes all of the even multiples too, right? Because that would be 1 pi, 2 pi, 3 pi, 4 pi, blah, 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 blah. That's what we have here. 1 pi, 2 pi, 3 pi, 4 pi, on down the line. This is just the 2 pi, 4 pi, 6 pi, but you see we already have those counted. So our critical values include any multiple of pi. So you'd probably write that as something like n pi or k pi or something like that. All right, so we can use these to actually find some absolute minimums and absolute maximums. And I talked about it a little bit in the last video about using your closed interval stuff. You test the endpoints and you look in them somewhere in between. So what we're going to do here, as long as it's continuous on the interval, we can just test the endpoints and test any critical points to find our absolute min, absolute max. Okay? So the first thing is, I want to find, where do I have critical points? So using the chain rule, this times, and now the derivative of the inside would just be 2x. Okay. Now, I want to factor these things. The x squared minus 1 is x plus 1, x minus 1, and that's squared, right? So we got 2 of each of those factors, and then times the 2x. So just to write it out a little neater, I'm going to write that as 6x there, because we get the 2 times 3. So our critical points then are at 1 and -1. So what I want to do is I evaluate the function at the endpoints and at the critical points. So I'm not going to do the -1 twice, okay, because, well, I'm too lazy for that. But if we evaluate the function at -1, that's going to be 0. At 2, it's going to be 27. And at 1, we're still going to get 0. Okay. So the absolute minimum is equal to 0, and that happens at x equals -1 and x equals 1 as well. And then the absolute maximum is 27. That happens at x equals 2. But if it just asks for the minimum value, we're just giving this one, right? The absolute maximum value is 27. I just put the at x equals 1 or whatever in case you happen to get asked something along those lines as well. All right, so one more of those. So find the absolute min and absolute max on the given interval. So that's from 0 to 15. So the first thing I actually want to check is this denominator and see if our function is actually continuous on that interval. So my question is, where is that equal to 0, and does it fall? Yeah, I got 10 minutes. All right, does it fall from 0, between 0 and 15? So will this thing factor? And the answer to that is no. You can't find two numbers that multiply to be 25 but add up to be -1. So I'm thinking about the quadratic formula again. 1 plus or minus square root of b squared minus 4ac. So that'd be minus 100 over 4a, or over 2a. So again, that's not real, so it's continuous. We're in good shape. I need to find the derivative. So the derivative of this thing times 1 minus, and then leave the numerator alone. The derivative of the denominator would be 2x minus 1 all over that denominator squared. So let's see. If I start combining my like terms, because this is -2x squared plus x, right? That's just times 1. So x squared, that's a -x squared, a -x squared, -x. Yeah, that'd be 0. And then we'd just have the 25. All right, so where's that equal to 0? So where's -x squared plus 25 equal to 0? And that would be at -5 and 5. So now going back to my original function, I'm going to evaluate the function at the endpoints and at anything in between there. The -5 isn't in this interval, right? So all I have to worry about is f of 0, f of 5, and f of 15. So just typing that into my calculator, we're going to wind up with 0 there. 1/9 here, and then 4/15. 3/47 here. Okay, so this is my maximum, this is my absolute minimum. All right, so maybe that'll help. I did try to give you some oddball examples, and my computer's about to shut down on me anyway, so that's perfect timing. All right, good luck.